Hello students, a very warm welcome. Today we'll be beginning with lecture 1 of alcohols, a new topic guys. So guys, we have already done a fair bit in organic chemistry, so we've built our base. So we'll be building more on that guys, and we'll be understanding this new topic of alcohol. Guys, in alcohol, we will cover the preparation reaction of alcohols. First of all, we'll be introducing you to it. Then we'll be covering preparation reaction of alcohols. After that, we'll be talking about the various physical and chemical properties as well guys. So let's get started. All right guys, introducing you to alcohols guys. These are organic compounds in which OH group is present, right? In which OH group is present directly attached with a carbon atom, right? A carbon atom to which an OH group is attached. So this OH group is the alcohol group guys, right? We know about this very well, right? These are hydroxy derivatives of alkanes and monoalkyl derivatives of water, right? We can say they are hydroxy derivatives of alkanes, right? Or they are monoalkyl derivatives of water. The general formula guys is CnH2n plus 1 OH, or we can say CnH2n plus 2 O, right? This H has come over here, so we can say CnH2n plus 1 OH or CnH2n plus 2 O guys, right? The hybridization state of carbon is of course sp3. There is no double bond or triple bond present, right? All the four are single bonds, I mean, for the carbon atom in an alcohol, I mean, right? The geometry is tetrahedral, right? The geometry will be tetrahedral because sp3 hybridization, right? So sp3 hybridization we know is tetrahedral guys, right? The bond length guys, the bond length of C single bond O is 1.42 angstrom, right? In these compounds, the C single bond O bond length is 1.42 angstrom. Guys, now a question for you. Will C double bond O, right? C single bond O has a bond length of 1.242 angstrom. Whether C double bond O will have a bond length greater than 1.42 or less than 1.42? This is your question. You have to think about it, guys, right? Let's move on. Next up, guys, these are of the following guys depending on the number of OH groups present, right? They can be monohydric alcohols, right? Contains only one OH groups. They can be dihydric, contains two OH groups, like example glycol, right? Glycol is an example where guys there are two OH groups present, right? Trihydric alcohols, right? For example, glycerol, right? Glycerol, it contains three OH groups, right? Polyhydric alcohols, right, contains more than 3 OH groups, right? For example, sorbitol, mannitol and so forth, right? Alcohol guys shows chain, position and functional group isomerism, right? It can show chain isomerism, position isomerism and a functional group functional isomerism guys, right? If there is a chirality present guys, if there is chirality present, that is there is a chiral carbon atom present, then it also shows optical isomerism guys, right? I hope you've understood this guys, right? And I'll move on. Next up, methods of preparation from alkyl halides. So alkyl halides is the first preparation method that we are going to talk about. Alkyl halides. Alkyl halides reacts with aqueous KOH or aqueous silver hydroxide, right? Or H2O and forms alcohol guys, right? So for example, this is, I mean, the whatever is capable of lending OH minus. So guys, we know OH minus guys is a strong base, right? It's a strong base, right? It's a strong base, it's a strong nucleophile guys. So what it will do, it will displace this X. It will displace this X. For example, this is a 1 degree, right? This is a 1 degree alkyl halide, right? This will, even though it's a strong base, it will undergo an SN2 mechanism, right? That is a different thing, right? But it will displace this X and form RCH2OH and KX will be formed, right? Over here guys, again OH minus will be present, and OH minus guys over here, what it will lead to guys, first of all you have to understand whether this will be SN1 or whether this will be SN2. Guys, AgOH is not a very, not a very strong base. This K plus OH minus is a more strong base. Although OH minus is present, this is aqueous AgOH, right, over here. So it might proceed with SN1 or SN2, it depends on the cases, right? But this is for certain that this X will be displaced over here, right? And OH will attach, right? I hope you've understood this guys, and the byproduct will be AgX, of course, right? Over here H2O, right? H2O is present. So guys, H2O is a base, right? I mean, it's a nucleophile, but it's a weak nucleophile. H2O in itself is a weak nucleophile, right? So guys, this reaction will proceed through the SN1 mechanism. Of course, a carbocation, a 3-degree carbocation will form over here. So this is 1 degree, this is 2 degree, and this is 3 degree alkyl halides respectively. So over here, the carbocation, this is for certain, will form, and then this will, attack over here, and this finally will be formed, and HX will be left as a byproduct, right? I hope you've understood this, guys. This is how, alcohol can be prepared from alkyl halides, guys, right? I hope you've understood this, guys. Apart from that, apart from aqueous KOH, we can also use aqueous NaOH, right? Now, preparing from alkenes, so addition reactions, we've already talked about this. Alkenes are catalytically hydrated by dilute mineral acid solutions, right? So, for example, if you have this ethylene over here, right? If you treat it with H2O in the presence of dilute H2SO4, guys, what will happen is that addition reaction, right? Electrophilic addition reaction will take place. We've talked about this in alkenes, guys. So H plus over here, right? This pi bond will attack over here, right? A carbocation will be formed either over here or over here. I mean, because this is completely symmetric, it can form any place, right? Then this H2O will attack over here, right? And this will be formed, right? CH2, CH3, right? And then there can be an OH over here, or we can alternately write it as CH3, CH2, OH, right? Now, guys, for example, over here, we've talked about this in quite detail in alkenes chapter, right? When we were talking about where will the carbocation form, the Markovnikov rules and the rule and all, right? So this, guys, the carbocation will form over here, of course, right? And finally, OH will be attached here, right? Of course, there is no possibility. This is a simple R group, right? So there will be no methyl hydride or anything shift that can happen, which can make the carbocation more stable. If there was a certain group present in R, right? If R was a certain group in which, a certain hydride or methyl or, chain expansion, right? Ring expansion can happen, right? Not chain expansion, ring expansion can happen. In that case, that will happen first. And a more stable carbocation and a more stable intermediate will be formed, and then the nucleophilic addition will take place. Of course, this is electrophilic addition reactions, and we've talked why it's called electrophilic addition reaction. It's called an electrophilic addition reaction, guys, because the electrophilic addition, the addition of the electrophile, guys, is the slowest step. It's the rate determining step, guys, right? I hope you've understood all this. Next up, oxymercuration, demercuration, important thing, right? Alkenes react with mercuric acid in the presence of water to give hydroxymercurial compounds, which on reduction yields alcohol, right? This is again Markovnikov addition, right? It proceeds the Markovnikov way, right? So first of all, Hg plus, right, will be added, right? Just like hydrogen is added, right? Where the number of hydrogen atoms are already more, right? That is where the hydrogen atoms were added, right? When we were treating with HBr, remember Markovnikov's rule, right? In the same manner, this Hg will attach where there are more number of carbon atoms, right? More number of hydrogen atoms, not the carbon atoms, the more number of hydrogen atoms, right? And on the other part of the double bond, there will be a carbocation form. It might rearrange, and finally, I mean, this is the after treating it with mercuric acetate, you will get this, and finally when you treat it with this NaBH4, this NaBH4 is a reducing agent, guys. It's a reducing agent, right? We know this. It's a mild reducing agent, right? NaBH4 is a mild reducing agent. It will be able to reduce this, it will be able to remove this HgOAc and finally attach H, and in the process give you an alcohol, right? I hope you've understood this, guys, right? So hydroxymercurial, this compound is reduced, right? And finally only alcohol is left, right? H is added, right? So this is oxymercuration, demercuration, and yes, we have obtained our alcohol, right? So mechanism, you can refer to the chapter of alkenes where we have discussed this mechanism in detail, right? How does this reaction proceed, guys, right? I hope you've understood this, guys. Next up, hydroboration oxidation, right? Hydroboration oxidation, guys, this is anti-Markovnikov reaction, right? This is of anti-Markovnikov orientation, guys. So what you might understand is anti-Markovnikov rule, I mean, it proceeds in a manner which is different to the Markovnikov way. I mean, it's not entirely different. The principle is the same, which is the stability of the carbocation, right? But guys, what happens in this Markovnikov anti-Markovnikov addition reactions is that the plus charge is formed in a different manner, guys, right? I hope you understand. You can refer to the alkenes chapter for a better understanding of that, right? Anti-Markovnikov rule, right? I hope you've understood this, guys. So when we treat it with diborane, guys, first of all, this trialkyl borane, this complex is formed. Trialkyl borane is formed, right? We treat it with diborane in hydroboration, guys. We treat it with diborane. This trialkyl borane is formed. Then we oxidize it. We oxidize it using this hydrogen peroxide. Hydrogen peroxide, guys, we know is an oxidizing agent, right? This is an oxidizing agent, right? So it will oxidize it, right? And we treat it in the presence of OH minus, right? In the presence of OH minus, we oxidize it. So what will happen is this will convert to this, right? And BOH whole thrice will be the byproduct, right? So again, we have obtained our alcohol. Guys, you can see it proceeds this time in the anti-Markovnikov fashion, right? Anti-Markovnikov addition is what you will observe over here, right? Two things, Markovnikov addition and anti-Markovnikov addition. This is the anti-Markovnikov reaction, guys, right? So guys, if you remember the principle behind it, if you remember the basics well and good, you will be able to figure out this thing very, very easily. Even if you don't understand the basics very well, if you remember, this is the anti-Markovnikov way of addition over here in this hydroboration oxidation, guys, then you will be able to get to the result as well, right? I hope you understood this, guys. Let's move on. Next up, by reduction of carbonyl compounds, guys. So carbonyl compounds can be reduced. For example, we can take LiAlH4. LiAlH4 is basically LAH, right? In the presence of Na and C2H5OH, right? In the presence of Na plus C2H5OH, right? So Na plus C2H5OH basically gives you C2H5O minus Na plus. So it basically converts this base into a nucleophile, a stronger base, right? A stronger nucleophile, right? So what will happen, guys? It will first of all reduce this. Right? So once it reduces, it will reduce this to a alcohol, guys, right? By reduction of carbonyl compounds. So 1 degree alcohol on being treated with this, right? Well, this ketone, this ketone when being treated with this, it gives a 1 degree alcohol. Similarly, guys, in this was the aldehyde, right? When aldehyde, guys, is treated with LAH in the presence of Na plus C2H5OH, it will give you a 1 degree alcohol. When a ketone is treated, guys, it will give you a 2 degree alcohol, right? Now, to note over here, we cannot obtain 3 degree alcohol from this method. We will not be able to obtain a 3 degree alcohol through this method. If we use NaH as reductant, then the process is called Darzin's process, right? If we use NaH as the reductant, right? Sodium hydride as the reductant, guys, the sodium hydride basically gives you Na plus H minus, right? We'll talk about this. Or for example, lithium hydride gives you La plus N. And when you use Na plus H minus, guys, this process is called Darzin's process, right? And this reagent is basically the Darzin's reagent, right? This is the Darzin's process of preparation of alcohol, right, from a carbonyl compound, right? Either a aldehyde or a ketone, guys, right? I hope you understood this, guys. Reduction of acid or its derivatives. So acid, carboxylic acid or derivatives like ester and so forth, guys. So what will happen over here? Again, if you treat it with LAH, right, it will give you an alcohol. It will give you an alcohol, guys, right? So basically, this will go and the alcohol will be left, as you can see over here, right? Similarly, you'll get an alcohol over here, right? Similarly, over here also, in case of an this is an ester, guys. When you treat it with LAH, right, lithium aluminum hydride, guys, right, in this case again an alcohol will be formed, right? So two alcohols will be formed, RCH2OH and R-OH, guys, right? Again, if you treat this with LAH, right, again reduction will happen and you will get this, guys, right? Important note, guys, acid amide does not form alcohol on reduction, it forms primary amine, guys. So acid amide, guys, does not form alcohol on reduction, it will form primary amine, right? It does not form alcohol, it will form primary amine on reduction, guys. So this is an important point that you should remember, guys. I'll just star mark it, right? Please remember this. If this ever, if this ever comes as an exception, for example, if you can remember this as a fact, and when for example, if it comes in an exam, it strikes you, you can mark the answer very easily, right. The mechanism, you can of course figure it out, right. Because there are certain different properties of the amide, the acid amide that will be present. So acid amide will be converted to amine, not alcohol. So basically the bond between C and N won't break in this case, right. I hope you've understood all this, guys, and I'll move on, right. Next is using the Grignard reagent, guys. So Grignard reagent we've already seen in many places, right. So Grignard reagent is again, right, a very widely used reagent, right. When you treat it with oxygen, guys, when you treat this Grignard reagent with oxygen in the presence of aluminium oxide and you heat it, right, first of all this complex will be formed, ROMgX, right. And when you hydrolyze it, right, ROH will be formed and MgXOH will be left out, right. MgXOH will be left out, guys, right. So remember RMgX, when you oxidize it in the presence of aluminium oxide and heat it, and then you finally subject it to hydration, you'll get an alcohol, right, and MgXOH will be formed with it, right. I hope you've understood this, guys. Now treating the Grignard reagent with ethylene oxide. So this is ethylene oxide, guys, we know this, do we? This is ethylene oxide. This is our ethylene oxide, right. When you treat it with this, guys, ring breaks, right, ring breaks, guys. So for this R minus will be able to attack this positive side, right. This bond will break, rearrangements will happen, right. So this now this O will come with a minus. So basically what you'll get is this R has attached over here, this CH2, then there is a O minus, right. The Mg plus X will get attached over here, right. O minus Mg plus X will get attached over here, guys. Now if you treat it with water, guys, this water will attack over here, right, and this OMgX will be able to leave, O minus MgX plus, right, and MgXOH will be able to, this O minus, in fact, this will not proceed like this, right. So first of all what you'll get is, you'll get this, right, RCH2CH2, right, O minus MgX, right. Now there will be HOH, right. This O minus will take this H, attack this H, right, it will attack this H, right. So it will first of all form MgX, right, OH, right, this will be formed, MgXOH will be formed. Now guys, OH minus will be left over here, this OH minus will attack this side, right, and you'll get RCH2CH2 OH, right. This is the alcohol that we have obtained, guys, right. Three-membered ring we already know is a very weak ring, right. It can be broken down very easily, guys, right. I hope you've understood this, guys, and I'll move on. Treating reaction with carbonyl compounds, how it can be prepared, guys. So again, Grignard reagent we've taken, right. Carbonyl compound, again this will have a delta plus, so this delta minus will attack over here, right. It will form R, right, it will form R dash C double bond O H, and then this H was over here, right. This double bond O has now broken down, right. So it will form this R dash C O, right. O minus will come over here, right. There was an H, and then this R that has attacked over here will come over here. This will become O minus MgX, right. Now when you treat it with water again, guys, this O minus will displace the hydrogen of this water, OH minus will be left, it will attack this side, and you'll finally get R, this R dash R, OH, right, and H, right. So this is exactly what we have over here, right. Just some things are up and down. We are not right now looking into the, for example, the stereoisomer or anything isomerism. We are not looking right now into this. We are just looking at the product, right. If R dash is equal to H, product will be 1 degree alcohol, of course, right. If R dash is equal to R, product will be 2 degree alcohol. If carbonyl compound is ketone, guys, product will be a 3 degree alcohol, of course, right. If the best method for, it is the best method for preparation of alcohol, because we can prepare every type of alcohol, guys, right. This is considered from Grignard reagent, right, reacting it with carbonyl compound, because we can prepare all types of alcohol, both 3 degree, 2 degree and 1 degree, guys, right. In this case, we'll be able to produce both 3 degree, 1 degree. So for example, if this was instead of this aldehyde, guys, if it was R dash C double C R dash C double bond O R double dash, guys, then in that case, of course, right, a 3-degree alcohol will be obtained, right? So 3-degree, 2-degree, 1-degree, all types of alcohol can be obtained with this method, right? Moving on, guys, preparation from primary amines, guys, right? Primary amines, when treated with this acid HNO2, guys, a strong enough acid, right, in the presence of HCl, guys, right? So what will happen is, guys, ROH, N2 and H2O will be formed, guys. Now this is not a very good method for preparation of alcohol, guys, right? So first of all, guys, you know, this H plus will attach over here, right? This will be NH3 plus group will be formed, right? Now the OH minus present in the aqueous solution, right, it will attack over here. I mean, the OH minus present will attack over here, right? It will lead to the formation of ROH, right? Perhaps N2 will be released from over here and water will be formed, right? All this will happen, right? This is how ROH will form basically, right? But it is not a very good method for preparation of alcohol because a number of byproducts are formed. So for example, when ROH is formed, guys, right, and then there is acid present, right? There is acid present and then there is Cl minus also present in the system, right? So what will happen is this might, you know, hydrate this. The Cl minus will now be able to displace this H2O, and then there will be some product, some RCl that will be formed, right? Alkyl chloride that might get formed, right? Or alkyl nitrite, HNO2, NO, for example, NO2 minus can instead, you know, displace this H2O from over here and form RNO2, guys, right? So all these side products that might be formed, so making the yield of what we require from this process, that is ROH, not very good, right? So this is, I mean, this is a point that you should note. It is not very good for the preparation of alcohol, right? In this reaction, we take ethyl amine, right? Then main product will be ethanol, while if we take methylamine, then the main product will be dimethyl ether, right? In fact, ether can also form, right, through intermolecular dehydration, guys, right? We've talked about all this, right? So ether can also be formed, right? So for example, if we take methylamine, right, if we take CH3NH2, guys, right, in that case dimethyl ether will be formed. That is the most stable product, that is the most abundant product that will be obtained in that case, that was observed, guys, right? I hope you've understood this, guys, why this is not a very good method, right? Next up, guys, an example over here, which of the following reaction is called, I mean, the Bouvard-Blanche reduction, guys. The reduction of carbonyl compounds through Na plus CH2,5OH minus, guys, to give our alcohol is called, in fact, the Bouvard-Blanche reduction, guys. So as you can see, reduction of carbonyl compounds through Na in C2H5OH is called Bouvard-Blanche reduction, guys, right? I hope you've understood this, guys, right? And I'll move on. Acid derivative which does not give alcohol on reduction, as which will be the acid derivative that does not give alcohol on reduction, guys. We've talked about this, guys, right? So amides, right? Acid amides do not give alcohol on reduction, right? Acid amides, right? This is, I mean, acid amides do not give, right? Acid amides, they do not give alcohol on reduction, right? Instead, guys, they give amines, right? We've talked about this, right? All right. So this is what we have. Acid amide primarily forms primary amine on reduction, right? So the major product will be a primary amine, guys, right? In which of the following reaction alcohol is not formed? Guys, over here, of course, we know that alkanes are paraffins. They have very, very low reactivity, guys, right? So even if, you know, you protonate it highly, right, you subject it to a very, very strong acid, it won't be able to give alcohol from over here, right? They are, I mean, they are saturated, they are paraffins, right? So this is, I mean, definitely wrong. I mean, this is the correct answer. It will not give an alcohol. Rest of them will give alcohol, right? I hope you've understood this. For example, if you protonate it over here, right, it will be able to give you know, for example, this alkene, right? If you subject it to hydrogenation, so high protons, I mean hydrogenation H plus, and then you have, you know, so a supply, for example, of you take NaH, right, sodium hydride or something, and you subject it, it will be able to give. For example, this H plus over here can also leave, right? So a variety of things can happen over here, right? Highly protonated, this will give you alcohol. So for example, in the first case, what will happen is this will form, right? This will form, and then an OH will attach over here, right? Similarly over here, RCOOCl, when it's subjected to LAH, lithium aluminium hydride, guys, right? This will give you in fact RCOH, right? Similarly over here, this is, we know, an acid derivative, so RCOO, right? Whole twice O, right? So basically this, right? This is like this. It will give you alcohol, guys. It will reduce and give you alcohol. I hope you've understood all this, guys. So definitely, guys, this will not be able to give you an alcohol. Moving on, guys. The next thing, to the next question. Physical properties, guys. Alcohols are colorless with a specific smell, right? They are colorless with a specific smell. They are generally liquids, right? They are soluble in water due to the hydrogen bonding, right? ROH, right? They will be soluble in water due to the hydrogen bonding present, right? I hope you understood this, guys. These are partially soluble in organic solvents as well, right? Not fully soluble, but partially soluble, right? They are liquid in nature up to 12 carbon atoms, and after that they become not liquid, right? Melting point and boiling point, right? Melting point and boiling point depends on their physical properties, right? For example, if they are symmetrical, if they are stable, then the melting and the boiling point will be higher. The molecular branch mass, guys, is directly proportional to 1 by the number of branches. That is, the molecular mass is inversely proportional. If there are same number of carbon atoms, guys, right? And we are talking about the molecular mass, it will be inversely proportional to the number of branches, guys, right? I hope you've understood this, guys. Boiling point of alcohol are higher than equivalent ethers, guys, right? Boiling point of alcohols are higher than it is due to the hydrogen bonding, guys. So ROH is generally present in what? For example, if you take an aqueous solution of it, there will be strong hydrogen bonding, guys. This hydrogen bonding, guys, this hydrogen bonding present among intramolecularly and intermolecularly. So what will happen, guys, is that between the same type of atoms, and also if there is an aqueous solution, not intramolecular, it's what I meant, it will always be intermolecular, right? Two molecules, right? So guys, two same type of molecules, or two alcohol groups, or between alcohol group and water, there will be strong hydrogen bonding that will exist, right? Which will make the boiling point higher than that of its the closed compounds that it has, which are ethers, guys, right? Alcohols are poisonous in nature also. Some alcohols are poisonous in nature also. Increases with increment in molecular weight or branching, right? So the poisonous character, the more complex the alcohol is, guys, the more the chances of it being poisonous will be, right? Ethanol is an exception, which is non-poisonous in nature. It is most useful organic solvent as well, guys, right? Ethanol, right? Ethanol is non-poisonous in nature. Methanol causes blindness, right? Methanol is something that causes blindness. Isopropyl alcohol is called as rubbing alcohol, right? Isopropyl alcohol, so whenever you rub it to certain portions, right, it has certain benefits. Cholesterol, right? Cholesterol is again an alcohol, is an example of complex alcohol, which is called notorious alcohol because it causes heart attack, right? So we know about cholesterol problems and so forth, right? Viscous nature of alcohol is directly proportional to the hydrogen bonding or the number of OH group present, right? How viscous it will be, right? I mean, the viscosity, right? I mean, if you talk about in terms of how consistent will something be, right? If you touch it, if you feel it, right, how viscous will it feel? I mean, that defines viscosity. I mean, there is a separate topic in not in physics, not in chemistry, but you'll study it in physics, right? How do you how do you measure viscosity and other things related to that, right? So but over here, viscosity, how viscous something is, right? It's directly proportional to the amount of hydrogen bonding or the number of OH group present, right? That is why we say alcohol is less viscous than glycerol and mannitol, right? Alcohol is less viscous than glycerol. Mannitol is more viscous than glycerol, guys, right? Alcohol is less viscous than glycerol. So glycerol is basically it has three, right? It has three. We talked about this, right? It has three OH group present, right? Glycol has two OH groups present, right? So simple alcohol is less viscous than glycerol, and mannitol is more viscous than glycerol, guys, right? Because there are more number of OH groups present, right? I hope you understood this, guys. Ethanol is liquid, while glucose is solid, right? uh, it is due to more hydrogen bonding in glucose, guys, right? I hope you've understood all this, guys. Moving on, guys, the remainder of the things we'll cover in the next class, guys, right? There is a lot to be covered in terms of, reaction with Na, chemical properties, dimethyl ether, and then we'll be talking more about the properties of alcohols, right? The various reactions this shows, right? We've talked about the preparation reactions. Now we'll talk about the various other reactions that these alcohols will show, right, in the coming lectures, guys, right? And there will be a lot to discuss about alcohols, right? So please, do your due diligence, maintain your notes, right? Try to remember things. So today, for example, we covered a lot of things, right? A lot of different things, right? For example, NaH and C2H5, in the presence of Na plus and C2H5, how it reduces certain things, how carbonyl compounds are get reduced, how acid and acid derivatives get reduced, right? These are the various things we studied. We talked about, reduction, we talked about, using Grignard reagent for preparation of alcohols, right? We, for example, saw in case of ethylene, right? Ethylene oxide, right? CH2CH2O, right? The three-membered ring, three-membered heteroatom ring that we talked about, right? How the Grignard reagent was useful over there to prepare something, certain things. For example, we also talked about, using HNO2 in the presence of HCl, guys. That again, that was not a very feasible method if you're, looking only to prepare ROH, I mean alcohol, because, a number of side products are also formed in that case, right? So for example, ether, right? If you remember, in a certain case, guys, there was methoxy ether that was getting formed, right? So all these things you should, understand, be ready for. We, for example, we talked about oxymercuration, demercuration, we talked about hydroboration and oxidation, guys. So one proceeds the Markovnikov way, the other proceeds the anti-Markovnikov way. So all this you should try to remember, right? Delve into mechanisms also that we'll discuss, right? Some of the mechanisms, anti-Markovnikov, we've already discussed in the chapter of alkenes, right? So revise everything, revise this chapter as well, and I'll see you in the next class.